Hi, welcome to the Olympiad geometry. Let's continue our study on geometry treasure. Today we're going to talk about the lattice point with specific angle. First, we'll give the definition of the lattice point. In a triangle, if all interior angles are integral times of 10 degrees, which means in triangle ABC, we know that angle A, angle B, angle C are the integral times of 10 degrees. And the angles formed by the sides and segments that connecting a certain inside point and vertices are integral times of 10 degrees, which means we have a point inside of the triangle ABC, let's call it D. And the angle formed by the sides and the segment that connecting this point to the vertices are also integral times of 10 degrees, which means these 6 angles are integral times of 10 degrees. We call this inside point a lattice point with specific angle. So this point is a lattice point with specific angle. You may notice that it's occurred in the past videos, in previous videos that I think we showed about three or 4 problems associated with this one, right? But each problem we use a unique method. So here is a question: how many problems are there can be like this form, right? And how can we solve them? Or is it possible to solve all of these kind of the problem using just one method? Right? We don't need to creatively to think about the solution. We just use one powerful and effective method. The answer is yes, but let's just think about this problem itself first. The thing we know that is angle A plus angle B plus angle C equals to 180 degrees, right? Which means we can define 3 integers. We want these 3 integers that A plus B plus C equals to 18. We can do that, right? And also we force A less or equals to B and less or equals to C, right? And then we can think of how many cases are there, right? So A can be 1, right? For the case A is 1, B can be 1, 2, 18 minus 1 divided by 2, which is 8.5, which means B can be from 1 to 8. There are 8 cases, right? If A equals to 2, that means B can be 2 to 18 minus 2 divided by 2, that is 8. So 2 to 8, which is 7 cases. And A can be 3, right? When A is 3, that means B is 3 to 7, which is 5 cases. A is 4, B can be 4 to 7, which is 4 cases. A can be 5, B can be 5 to 6, which is 2 cases, and A can be 6. B can only be 6, C is 6, which is 1 cases, right? And remember that D is a point that makes inside the triangle ABC, which means the angle A, angle B, angle C, at least it should be 20 degrees, right? At least to be 20 degrees. So all of these cases are invalid, which means we have all of these cases that existing the lattice point with specific angle. And how many cases are here? 7 plus 5 plus 4 plus 2 plus 1, which is 19. So we have 19 cases here, but for some triangle, they have multiple lattice points, right? So the total cases would be 45, I think. And I'm not going to expand this to be a 45 problems, right? I'm going to just show one method, which we should be familiar with. Let's show an example here. So a problem example here is that in the triangle ABC, angle B equals to 60 degree, angle C equals to 40 degree. P is a point inside the triangle ABC, and angle PBC equals to 20. So let's draw it first. Angle PBC equals to 20, right? And angle PCB equals to 30, which means it's a little larger than the angle PBC. So here is C, this one is P. And we already know that angle B is 60 degrees. That means angle PBA is 40 degree, right? So 40 degree here. And because angle PCB, this one is 30 degree, and angle C is 40 degrees. That means angle PCA is only 10 degrees. So we can draw it like this. This is 10 degree, and here is 20. This one is 40. This is A, and we connect AP. Right, that's a problem. And we want to prove angle PAB equals to 70 degrees. Basically, it's asking us to find the angle PAB and angle PAC. Right, we know that angle PAB plus angle PAC equals to 180 degree minus 60 minus 40, which is 80 degree. Right, that's what we know here. Nothing about the angle form of Sievert theorem. We can use it, right? Because the AP, BP, CP are concurrent on the P point. So we can directly write the Sievert theorem with angle form, which is sine angle BAP to sine angle PAC times sine angle CBP to sine angle PBA times sine angle ACP to sine angle PCB equals to 1. That's what we have from the Sievert theorem, right? And we know that we want to find the angle PAB, which is angle BAP, and we want to find the angle PAC. So we want to find these two angles, which means we have this equation and this equation to find these two angles. So we can replace real data here, which means the sine angle BAP to sine angle PAC times sine angle CBP, which is sine 20, to sine angle PBA, which is sine 40, times sine angle ACP, which is sine 10, to sine angle PCB, which is sine 30, equals to 1, right? And we know that this is 0.5. And look at here, we know that sine 40 can be rewritten as, so we have BAP to sine angle PAC times sine 20 times sine 10 to 2 sine 20 cosine 20, right? That's a sine 40, and times this one equals to 1, right? So these two cancels, which means we know that sine angle BAP to sine angle PAC equals to sine 10 to cosine 20, right? And we notice that sine 10 to cosine 20 is sine 10 to sine 70, right? And 10 plus 70 is 80. That is saying the angle BAP is 10 degrees and the angle PAC is, the angle BAP is, did I write it wrong? Let me see. Yeah, this is wrong, right? Should be flipped. Right, let me rewrite it here. Sine angle BAP to sine angle PAC equals to cosine 20 to sine 10, which is sine 70 to sine 10, right? That means the angle BAP is 70 degrees and the angle PAC is 10 degrees. The angle BAP is 70 degrees. Okay. So I also want to show the cases that in one triangle we might have, in one triangle, right? We might have multiple lattice points, like I show here in problem example 2. In triangle ABC, the angle B equals to 40, angle C equals to 30. P is a point inside the triangle ABC and angle PBC is 30. So the angle PBC can be 30 degrees. And angle B is 40 degrees, right? So we have the case prove that if angle PCB equals to 10, then angle PAB equals to 10. If angle PCB equals to 20, then angle PAB equals to 40. Okay, so angle PBC is always 30 and angle B is 40. That's what we know here. And let's draw the figure for the first case that angle PCB equals to 10. So it's pretty small here. Right, that is angle PCB. This is 30, this is 10 degrees. Right, and we know that angle B equals to 40, which is 10 degrees here, and angle C equals to 30, which means angle PCA equals to 20 degrees, right? So roughly say this is 20. And now we want to find the angle PAB. We want to prove that angle PAB equals to 10. And we know this is 10, right? Because this angle B is 40. So similarly, we use the exact same method here. We know that sine angle BAP to sine angle PAC times sine angle CBP to sine angle PBA times sine angle ACP to sine angle PCB equals to 1. So sine angle BAP to sine angle PAC times sine angle CBP, which is sine 30, right, to sine angle PBA, which is sine 10, times sine angle ACP, which is sine 20, to sine angle PCB, which is sine 10. We know it equals to 1. And another thing we know is that angle BAP plus angle PAC equals to 180 degrees minus 40 minus 30, which equals to 110 degrees, right? Now look at this one. We can use the same way, right? The sine 20 can be extended to be 2 sine 10 cosine 10, and the sine 10 cancels, and the 2 cancel with this half. So we have cosine 10 divided by sine 10, which means the sine angle BAP to sine angle PAC times the cosine 10 divided by sine 10 equals to 1, which means it equals to sine 10 divided by cosine 10. Right. So think about cosine 10. Cosine 10 can be rewritten as sine 90 plus 10 right? 90 plus or minus 10. Right, here we use plus just because we need angle BAP plus angle PAC equals to 110. This is a solution, the 110, which means angle BAP equals to 10 degrees. Right, that's the first case. And for the second case, the angle PCB equals to 20, and we want to prove that angle PAB equals to 40. Notice that angle PCB is 20, so here is 20. That means the angle ACP is 10 degrees. So we just need to flip these two, right? So for the second case, we have that sine angle BAP to sine angle PAC times sine 30 divided by sine 10 times sine 10 divided by sine 20 equals to 1. Right? So for this case, we know that sine angle BAP to sine angle PAC equals to sine 20 to sine 30. Right? And the problem is that 20 plus 30 does not equal to 110 degrees. Right, so we have to reform this one. Okay, notice this one is 0.5, which means this can be rewritten as twice of sine 20. Right, that equals to twice of sine 20 cosine 20 divided by cosine 20, which is sine 40 divided by sine 70. And we know that 40 plus 70 equals to 110, which means the angle BAP equals to 40 degrees. Angle PAB equals to 40 degrees. Right, that means in the same triangle ABC, we can find the 2 points that satisfy the 2 points as a lattice point with a specific angle. Okay? So this just show you how to solve this kind of problem, just because this point in the problem set, it already tells you that this point is inside the triangle ABC, and we want to connect the PAPBPC. That means the PAPBPC already concurrent on one point, so we can use the Silva theorem. Okay, and for the problem example 3, in the triangle ABC, D is an interior point if angle BAD equals to angle DAC equals to beta. Right, angle BAD equals to angle DAC, which means DA is an angle bisector. D is on the angle bisector of angle A, right? So let's just draw A. We have a triangle here, and let's call it A, B, C. So D is on the angle bisector, and we know that angle ABD equals to alpha. So this one is alpha, this is D, and this one is beta, this one is beta, right? Angle DAC equals to angle DAB, or angle BAD equals to angle DAC equals to beta. And angle ABD equals to alpha. Angle BCD, this angle equals to 90 degrees minus alpha minus beta. Now we want to prove that angle ACD, this angle, equals to alpha. We want to prove that this angle equals to this one. we can set this as angle x, right? Oh, let's say angle gamma, right? So we want to prove that angle gamma equals to angle alpha, and just use angle form of the Sylvus theorem. We know that sine angle ABD to sine angle DBC times the sine angle CAD to sine angle DAB times the sine angle BCD to sine angle DCA equals to 1. Right, we know this is true, and sine angle CAD to sine angle DAB, that's all sine beta, so this is gone. And what we have here is sine angle ABD, which is sine alpha, to sine angle DBC, right? Sine angle DBC. And times sine angle BCD, which is sine 90 degree minus alpha minus beta, to sine angle DCA, which is sine gamma equals to 1. We know this is true. Right, and we want to prove that gamma equals to alpha. The first thing is that we need to find the angle DBC. Okay, just because this is 2 beta, this is alpha, this is gamma, this is 90 degree minus alpha minus beta. So we know that the angle DBC is 180 degree minus 2 beta minus alpha minus gamma minus this one. So minus 90 degree plus alpha plus beta, right? So these two cancel. We know it equals to 90 degree minus beta minus gamma. Right, that is this one. So we have sine alpha to sine 90 degree minus beta minus gamma times sine 90 degree minus alpha minus beta to sine gamma equals to 1. Right, we have this one, and this one can be rewritten as cosine beta plus gamma. This one is cosine alpha plus beta. So we have sine alpha, cosine alpha plus beta equals to sine gamma cosine gamma plus beta. Right, we have this one. And we can extend it, right? Sine alpha times cosine alpha plus gamma, which is half of sine, this one plus this one, right? So that is 2 alpha plus beta, and plus cosine this one minus this one, which is cosine minus beta. No, should be sine, right? Yeah, should be sine. Should be sine minus beta. It equals to half of sine, this one plus this one, 2 gamma plus beta, and plus sine, this one minus this one, which is minus beta. Right, and we know these two are equal, so we cancel it, which means we got sine 2 alpha plus beta equals to sine 2 gamma plus beta, right? So gamma should be, that means we need to have that this one equals to this one, so gamma should be alpha plus k pi. And we're talking about these angles in one triangle, so there's k should be 0, which means gamma equals to alpha. right? So here basically we just use Silver theorem. We can solve all of these kinds of problems that relate to the lattice point. Okay, so again, the lattice point, the definition of the specific angle here is the lattice point. We use integral times of 10 degrees, but it doesn't necessarily to be this one. You can define it like what we have in the problem 3, right? It's still a specific angle, or specific point with some specific angles, right? We want to prove something. Okay, so basically in this problem we just in this video we just show all the like a general method, general solution for all of these problems. I hope you like this video, and if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. Thank you. See you in next one.